I will. I'm sorry, it doesn't work. Yeah, I will go very quickly at the start of presentation with some examples of our international collaboration, and then Adam will show you what we would like to do in our lab, maybe in international collaboration too, in area of investigation of using machine learning for quality control of additive technologies. We have a small international team in our research center, which is equipped with EOS equipment. We have open licenses for some metals. Our equipment, our machine is equipped in situ monitoring of EOS company, and we are developing our in situ monitoring systems to understand the process more. For R&D, it's very important we are able to collaborate with other labs in our RTI Research Institute, and we can collaborate with testing, investigating surface treatment, etc. And partnership is very important for us because team is not too huge, and we need the collaboration. Our local collaborating research institution, TZU Pilsen, translation is Research and Testing Institute. Pilsen is very well equipped for different industry, and one part of this is a department for thermal spraying, including all technologies for these technologies, including the application of cold spray. And I will start with my idea. I try to push to the European Commission because I think that some parts are or will be produced by additive manufacturing, and some of them will need improvement of surface from different reasons, to be more hard, to be better in abrasion, to have some thermal barriers. Sorry, European Commission didn't accept our proposal, but we were very, very hard working on this topic, and we obtained money from smaller European program, ERANET, with a smaller team. It was a team composed by Pilsen, Germany, and Poland. I will not comment the result. You can find it on website of this program and in some literature. 5 years ago, visited us Professor Nima Shamshay from University Auburn. We tried to develop some collaboration. We asked Czech government for money, but Czech government don't accept our proposal. But we use our internal money for this type of collaboration, and we perform investigation for Inconel 718, which was tested in fatigue, but test specimens were different various post-surface technologies we use at our RTI technology. In Trento, I discussed with Professor Nima that we would like to continue in our collaboration. Maybe we will prepare something similar, investigation, but with multi-axial loading. Because still, I think not only I, my friend Vladimir too, that multi-axiality is very important aspect to investigate at additive manufactured components. Because to produce something by this technology and to be economically in line with the castings and forgings must be components with a topological optimization. And topologically optimized component will have a lot of notches, and some of them will be multi-axially loaded. We have solved small project together with University in Bratislava. This workflow I have shown, I think 3 years ago in Porto, but still we didn't present results in detail in any paper. Shortly, it's possible to describe the project that we produced the test specimen, tested the test specimen uniaxially in torsion and different combination. Then we were able to compare experimentally and theoretically stated fatigue life and to evaluate different various multi-axial criteria which are overestimating or underestimating, or are in line with experimental results. Knowledge of the project we use with optimization, some industrially used components, some examples you can see on this picture. Now, we are preparing a lot of collaborations. I prepare collaboration with Unisalerno. We will investigate the Greek growth of CT specimens. We are preparing collaboration with Uniparma. We would like to continue our project with Bratislava by testing the component like test specimen on our multi-axial test stand, and I hope that our friends from Parma will have possibility to validate their new approach to the multi-axial fatigue life prediction. And now I would like to ask my colleague to continue and to propose something. Oh, sorry, this is not right.
So, good afternoon. My name is Polansky. I'm also from the University of West Bohemia. And today I'll show you some usage of machine learning for control quality in SLM. First, let me introduce the members from the team, starting with my supervisor, Ivana Zetkova, Mr. Ivan Gruber from company Amitia that is focusing for AI applications, and my colleague, Zubakir. As Mr. Kepka showed, we are using SLM machines where the quality of printed part is given by several factors such as laser parameter, scanning strategies. There are differences when using new, used, or recycled powder, or there are differences when using hard or soft recorders. And this all is closely related with the field we are focusing on, and that's specifically monitoring the powder bed, respectively monitoring the quality of spread layer. In following slides, I'll be using these images. That's basically top view cropped image of the powder bed. And to make it more clear what we are working on, I will introduce some common defects occurring while spreading a new layer. The first one here occurs when the recorder is spreading the layer and hits some elevated part, resulting in vibrations, and it creates these patterns called waves. And these are basically spots of thin and thick layers of powder. Second, recorder streaking. This happens when the recorder blade itself is somehow damaged, when a small piece is chipped off, or when the recorder blade catches some debris or particle and spread it along the platform. And the last one are some spots of missing powder, and this usually occurs on the edge of specific geometry, complex geometry. I also have an example. This is kind of extreme situation when we printed tall, thin parts, and one of them elevated, and in a few seconds you will see that it started colliding with the recorder blade, and it resulted in a catastrophe in file. So we decided to somehow screen or monitor this. So in our initial experiment, we trained a model that performs binary classification of the images. Basically, we have input images. These are the images of the powder bed after recoating, and then the model decides if the layer is well or not well spread. Here you can see some example of well and not well spread layer. And we used in total over 2,000 images to train the model, reaching 97% accuracy. However, this approach doesn't count with the position of the part on the platform. It doesn't count with the position of the defects. So now we are currently working on defect segmentation, which will be much more useful in our future work. And this basically highlights the defects and can also tell us more about the defect. We are also trying to implement some other sensors, such as accelerometer, to get more detailed information about vibrations while printing. I mean, vibrations from recoder. We are also using optical tomography from EOS to monitor heat. That's a field of my colleague Yusuf Bakr I showed on the beginning. And for us, it's very important to connect these defects occurring in layers and connect it with the real defects in material, how it affects the material. For this, we are using margin steel MS1 from EOS. And here I have one of the first results on the right picture. You can see some unmelted particles, you can see cracks. And this occurred when there were presence of defects, the waves. But this is just first result, and we will focus on this more in the future. And the general aim of the project is to train a model that will somehow predict the defects in material based on the input data, which is mainly the powder bed images, other sensors, and the optical tomography. We are very open to any kind of collaboration. Also, we are open to share the training codes. So maybe if you have some images, if you are collecting, if you are screening your prints, we are open to share the code, so we can try to train our own. And I would also like to say thanks to supporting the project by Ministry of Education, and thank you for the attention.